Hello, and this is Math with Beth, and we are going to be learning how to tell if a function is continuous. And the trick with this one is it's a very specific way to do it, and instructors are going to usually be pretty picky about how you write everything. So definitely listen to how your instructors want you to write this, but at least I can maybe help it make a little more sense. So here's the definition of telling if a function is continuous at a point. A function f is continuous at x equals a if. So there's three things that have to happen. And so when you explain this on a quiz or a test, you're going to have to show that these three things are happening. You can't just say, yeah, it's obviously continuous there. So the first thing is that f of a exists. So that means the input a, whatever number it is you're trying to prove that it's continuous at that point, that number needs to be in the domain. So that means it's not a whole, it's not an asymptote, nothing funny is happening at a. Okay, so that's step one, that f of a actually exists. The next is that the limit of x approaching a also exists. So remember, for a limit to exist, it has to be the same number approaching from the left as approaching from the right. So something like this, if I was looking at this point right here, this limit would not exist because from the left, it's approaching one number, from the right, it's approaching something else. So this would not work. You have to prove that the limit does exist. And then finally, if you've already proved that f of a exists and the limit of f of a exists, both at this certain number a, then the last thing you have to show is that they equal each other. So whatever answer you got for f of a is the same answer you got for the limit as x approaches a. So if that happens, then you can say a function is continuous over an open interval L if it is continuous at every point a in L. If f is not continuous at x equals a, we say that f is discontinuous or has discontinuity at x equals a. So this would be an example of something that is discontinuous at a certain point, because at that point we would have to jump from here to up here. So it's obviously not continuous. Okay, so let's try one. So is this continuous at x equals 3? Well, let's just go ABC. So first, does f of x exist, which in this case is 3? Yes, f of 3 does exist because hopefully most of you know that this is a parabola that is definitely continuous everywhere. And at 3, it would just be 9 minus 5, which is 4. So f of 3 equals 4, which means it does exist. Check. Next, let's check that the limit exists at 3. Well, again, if you wanted to graph this, you would know that it is a parabola. So yes, the limit at 3, we're definitely going to approach the same number from the right as the left, and that number is going to be 4. So the limit as x approaching 3 of f of x equals 4. Well, if this exists and this exists, then the last thing we need to explain is that they equal each other. So f of 3 equals the limit at x approaches 3 of f of x, which both equal 4. So this is where your instructors are probably going to be specific on exact wording. So don't get mad at me if they don't like this wording. So definitely check with your instructor here. But now hopefully you at least understand what we're doing here. Proving that the graph does exist at 3, that the limit also exists at 3, and now that those two things equal each other. So therefore, f of x is continuous at x equals 3. Something like that. Okay, let's try another one. So this is a piecewise function that happens to be switching from one thing to another at -2, and that is where we're checking. We want to check if it's continuous at -2. So let's go through the same three steps. So remember, A was, does f of x exist? So in this case, does f of -2 exist? Well, with a piecewise function, we have to check if we're plugging it into this part of the equation or this part of the equation. -2 would fall into, sorry, -2 would fall into x being greater than or equal to -2. So we're plugging it in to -2 minus x, which is -3, which means yes, it does exist. When we plugged in -2, we got -3. Next, does the limit exist? Well, in order to prove that with a piecewise function especially, you need to prove that the limit from the left side is the same as the limit from the right side. So in this case, coming from the left really means using that top equation. So to find the limit at 2 of f of x, we need to plug -2 in to that top function, which in this case gives us -1 plus 3, which is 2. The limit as x approaches, sorry, make sure you have a negative here too. We want to approach -2 from the left. That's what this is. Now we want to approach -2 from the right, which means we'd be coming from this way. So we'd have to use the other equation, which we've already done. I got -3. So the limit from the left did not match the limit from the right. So that means the limit as x approaches -2 of f of x does not exist. So we don't even really need to go to part C because all three things have to work for you to say it's continuous. So you can say something along the lines of, since the limit as x approaches -2 of f of x equals dne, the graph of, I just realized this is called g of x. So let's just be proper here. Sorry about that. Since the limit as x approaches -2 of g of x does not exist, the graph of g of x is discontinuous at x equals -2. Again, disclaimer, check with your instructors on the exact wording they want you to use, but that's the general idea. If one of these doesn't work, or they both work, but at the end they're not equal to each other, then you cannot say the graph is continuous at that function. So hopefully between whatever you're learning in class and this, you can now put that together and understand what your instructor wants and exactly how they want you to write it. If you have any questions on that, please let me know.